All right, let's go ahead and get started. In our last installment, we looked at the calculation of Q and how it related to K. And we talked about how Q is going to determine the direction of the shift in the equilibrium. So let's actually do a calculation of Q so that we can actually get experience in using Q to determine the direction. So here we go. It says Kc for the reaction is 19.9. So they're giving me the Kc for this reaction. It's Cl2 gas plus F2 gas in equilibrium with ClF. And that, of course, is a gas, right? So 1 to 2 mole to mole to mole relationship. It says find the equilibrium concentrations of all species if the initial concentrations of all species in the initial concentration, if the initial concentration of Cl2 is 0.4, F2 is 0.2 molar, and ClF is 7.3 molar. So I'm going to begin with a Rice table. So here we go. R is, of course, just the reaction. We have Cl2 plus F2 in equilibrium with 2 ClF. They've given me these initial concentrations of 0.4, 0.2, and 7.3 molar, respectively. But the question becomes, in which direction does the shift occur? Is it left or right? Or maybe not at all. Maybe I'm at equilibrium. Well, let's check. To do that, what I'm going to need to do is I'm going to need to do kind of a side calculation. We've got Q is equal to 7.3 squared over 0.4 divided by 0.2. This is the number that I get, 666. So obviously that's a much larger number than the K that I was given, right, of 19.9. So that means the shift is going to occur to the left, right? The shift is going to go left so that the equilibrium can be reestablished, right? So now what I'm going to do is I'm going to determine now that I know that I'm shifting left, I can put a plus right here, a plus right here, and of course on the other side that's a negative sign. 1, 1, 2 means I'm going to have a 1, and a 2 in front of those x's. So in this change column, I'm going to have plus x, and minus 2x. So the equilibrium line then, the equilibrium line is going to be the sum of the initial and the change line. So 0.4 plus x is 0.4 plus x, 0.2 plus x is 0.2 plus x, and 7.3 minus 2x, 7.3 minus 2x in that equilibrium line. All right, so looking good so far. Now let's just write an expression for K. So K is equal to 7.3 minus 2x. Actually, let's just write the expression first. So it's ClF. Remember to square that because there's a coefficient in front of that ClF of 2. We'll divide that by Cl squared and then divide again by F2, right? The two reactants. There's no coefficient, so there's nothing in the power or exponent position. So we're going to write now we're going to go from the expression to plugging in actual numbers. We've got 19.9 is equal to 7.3 minus 2x squared divided by 0.4 plus x, that's from here, divided by 0.2 plus x, that's from here, okay? Now, I'm not going to go through the mathematics of calculating this. I'll let you do that. Remember to use quad form if you've got it on your calculator. But here's what I got. I got x is equal to 0.925, all right? Now, that's not the concentration. Remember, we were asked for individual concentration. So just because you got the x doesn't mean that you're done. You have to plug those in. So when we plug in, let's start with ClF. When we say 7.3 minus 2 times 0.925, I got this number. Check this on your calculator. I got 5.45 moles per liter. For Cl2, that's this one right here, we have 0.4 plus 0.925. I got 1.13 moles per liter. So that's the Cl2. And then finally the F2. F2 is 0.2 plus the 0.925, and I got 0.133. It's a pretty sophisticated problem. It kind of integrates all the aspects of what we need to know how to do the Rice table, how to determine the direction of the shift, how to use quad form. All that went into this problem. So I think it's an important one. Okay? All right. Let's take a look at this problem now. It says Kc is equal to 170 at 298 degrees for this reaction. Again, the temperature is not important other than the fact that if the temperature changes, the K changes as well. But they're telling me that the Kc is equal to 170. And the reaction is 2NO2, and that's gas, in equilibrium with N2O4. Now, the question then is this. It says, suppose the initial concentrations of NO2 is 0.015 molar, and the concentration of N2O4 is 0.025 molar. Determine the equilibrium concentrations of all species, well, of the NO2 and the N2O4. So again, we start with the Rice table. So there's the R, 2NO2 in equilibrium with N2O4. The initial concentrations are given, 0.015, and let's see, 0.0025. Is that right? Folks, this is a typo right here. This should be, let me fix this for us. This should not be 0.00. This should simply be 0.025. Let me change that to make it correct. All right, so 0.025. Again, let me get my eraser here and fix that just like that. Apologize for that. There we go. So now we're fixed. All right, so 0.025 for the N2O4 concentration. Now again, we don't have any idea which way the shift is until we calculate the Q. So let me do that. So Q is equal to products over reactants. So 0.025 divided by 0.015, that'll be squared, of course, because the coefficient in front of the NO2. And when I do that, I get 111, right? So Q is equal to 111. So obviously Q is less than K. I was told that K is equal to 170. So because Q is equal to is less than K, I need more products. The shift is going to be to the right. Okay, it's going to be a right shift in this case. So that'll put a plus on the right-hand side and a negative on the left-hand side. The 2 is because the coefficient in front of this, NO2. And so we have minus 2x here and plus x there. So now let me just add up the initial concentration and the change row, 0.015 minus 2x and 0.025 plus x, just like that. Okay. And by the way, I'll never use this Q again. I'm not going to need it anymore. I only needed it for the purpose of telling me the direction of the shift, and it was to the right. All right, so now let me calculate the K. Let's do that. Well, K is equal to N2O4's concentration, that's the product, divided by NO2 squared. So this is the equilibrium expression. Now let's plug in. We were told that the Kc is equal to 170, so 170 is equal to, let's pull from the Rice table 0.025 plus x over 0.015 minus 2x. That value is squared. Now that's obviously going to be some algebra that's involved. So I'll save you the time. You can do that on your own for homework tonight. But for right now, let me just tell you that x is equal to 0.00128, right? Again, don't use, if you can avoid it, don't use the Pythagorean or the quadratic formula, but rather use quad form. And so x is equal to 0.00128. Now you're not done yet. Remember, the question was, what are the equilibrium concentrations? So in order to get those, what you're going to need to do is plug in. So for the N2O4 concentration, that's what I've got right here. I've got 0.025 plus 0.00128. I get 0.0263 moles per liter for the N2O4, and then for the NO2 I get 0.015 minus 2 times this value, and I get 0.0124 moles per liter, and that'll do it for that problem. Okay? All right. Now let's take a look at a problem that is very interesting because it involves a solid. The decomposition of a solid into gas. It says Kc for the decomposition of ammonium hydrogen sulfide is 1.8 times 10 to the minus 4 at 298 K. So here's the reaction. It's NH4HS solid in equilibrium with NH3 gas and H2S gas. It says, when the pure salt decomposes in a flask, what are the equilibrium concentrations of the NH3 and the H2S? So here's how the Rice table is going to happen. So the reaction again is NH4HS. It's in equilibrium with NH3 plus H2S. Now the initial concentrations of the NH4HS doesn't enter into the Rice table at all because it's a solid, right? It's a solid. So we don't care how much solid there is, so we're just going to put an X there. But initially, there's no ammonia gas, nor is there H2S gas, so we're going to have a 0 here and a 0 here as well. So the NH4HS is going to decompose into a gas, right, or into gases. Not very much gas, because the K value is very small, but there's going to be some decomposition, so even a little X is going to add to the zeros, right? So the equilibrium line then is going to read simply 0 plus X is X, 0 plus X is X, and now we can plug into an equilibrium expression. So K is equal to H2S concentration times NH3 concentration divided by, remember, there's no NH4HS concentration, right? It's a solid. So we're just going to put a 1 down there. You don't even have to put that if you don't want to. So now I've been told that the K value is 1.8 times 10 to the minus 4. So that's equal to, well, each of these is X, so I'll just call that X squared. When I take the square root of that, I get this number. I get 0.0134. So that then is the concentration then of both at equilibrium, the NH3 gas and the H2S gas. All right, so that takes care of that problem. Let's go to the next one. Actually, let's go to the next one. All right, the second part of this problem is exactly the same, except that we're going to start with some amount of ammonia gas already in the container. So we're not starting completely empty. So here's what the problem, or part B, says. It says, if NH4HS is placed in a flask already containing 0.020 moles per liter of NH3, and then the system is allowed to come to equilibrium, what are the equilibrium concentrations of NH3 and H2S? So this is an interesting one because we've already got some ammonia in the container. So let's write our Rice table. We've got R is NH4HS in equilibrium with NH3H2S. And again, remember that we had a previously added an amount of 0.02 moles per liter of the NH3, and then of course we had none of the H2S. Remember, NH4HS is a solid, so we'll just make an X through all of that. So the change then would be this. If this is 0 on this side, you have to shift from left to right, okay? So we've got plus X on this side, plus X on this side, nothing on this side, right? It's a 1 to 1 to 1 mole to mole to mole relationship. So for the equilibrium row, let's just add things up. 0.02 plus X, and 0 plus X is X. So that gives us that equilibrium row. Now let's write the equilibrium expression. So it's not quite as easy as the first time because we're going to have to add this complication right here. We've got K then is equal to the equilibrium concentration of NH3 times the equilibrium concentration of H2S. So we've got 1.8 times 10 to the minus 4, that was the K value that was given to us, was equal to, and now the new equilibrium concentration expression is 0.02 plus X for the NH3, and of course it's still X for the H2S. So now let's just do a quadratic. We've got 0 is equal to X squared plus 0.02X minus 1.8 times 10 to the minus 4. Remember, you've got quad form now, so make sure that you use that value, or use that program. So the X that I get is 0.00673. The alternate X was 0. This is actually a negative. Make that a negative. So that would mean this is not possible, right? So the X I'm going to use is 0.00673. That would give me equilibrium concentrations of H2S of 0.00673 moles per liter, and ammonia would be 0.0267 moles per liter. That'll